Welcome to Minimal's Tech. Starting from this episode, I will be creating a series of introductory tutorials on blockchain. These tutorials are based on a summarized synthesis of the blockchain public course at Nanyang Technological University. They are intended for non-profit purposes. If there is any infringement, please contact us for removal. Since the day currency was invented, humanity has been pondering a question. What is the nature of currency? Currency as a general equivalent serves as a medium of exchange for goods. It is a unit of account, used to mark the price of goods. It is a media for storing value. All of the above are backed by trust. The essence of currency is trust. Fiat currency is backed by the trust of the government. Due to the high centralization of a fiat currency, the government has the right to issue an unlimited quantity of currency through quantitative easing. Once the gate of unlimited quantitative easing is opened, fiat currency depreciates, leading to the loss of its trust. The advent of digital currency has greatly improved the efficiency of fund settlement. The double spending problem. Digital tokens consist of digital files that can be copied or forged, making it possible to use the same digital token multiple times. To solve the double spending flaw, banks track the count for digital currency through central computer systems. Due to the inherent defects of high centralization, fiat and digital currencies cannot fundamentally solve their underlying trust issues. In October 2008, Satoshi Nakamoto proposed the concept of Bitcoin. Bitcoin is a decentralized, encrypted digital currency. Cryptography is used to regulate the generation of currency units and verify fund transfers, operating independently of central banks. It can be sent over the internet, stored in digital wallets, addresses, and stored permanently and anonymously on the network. The invention of Bitcoin fundamentally solves the trust flaws of traditional currency. Satoshi Nakamoto himself remains mysterious to this day, and no one has ever seen him in person. The difference between Bitcoin and banks fundamentally lies in transparency versus opacity, and decentralization versus centralization. Traditional banks use a centralized ledger. It requires dedicated bank employees to perform bookkeeping operations. For example, in traditional centralized transactions, first step, Alice offers to buy a Raspberry Pi motherboard from Bob. Second step, Alice pays the money to Bob's bank account. Third step, the bank receives the money and notifies Bob, who then delivers the motherboard to Alice. Fourth step, after the transaction is complete, Bob can withdraw the money from his bank account. A decentralized network allows every node to have a copy of the ledger and jointly maintain it. In contrast to traditional centralized transactions, decentralized transactions follow these steps. First, Alice offers to buy an item from Bob. Second, Alice sends a corresponding number of tokens to Bob's digital wallet address and assigns with a private key. Third, Alice's transaction is published to the blockchain. Fourth, once confirmed by the blockchain, Bob can use his private key to extract the tokens sent by Alice from the digital wallet. Traditional centralized transactions often lack transparency, relying on intermediaries whose many operations are not disclosed, lacking a trust foundation. In contrast, decentralized transactions fully disclose the flow of funds and the transaction mechanisms. Once a transaction is completed, it cannot be tampered with. This transparent trust mechanism allows both parties to discard third-party intermediaries and achieve peer-to-peer transactions. Web 2 is a centralized system infrastructure network that enables high-speed information exchange. In contrast, the decentralized network represented by blockchain, Web 3, values trust above all. The invention of Bitcoin has made the foundation of trust in digital finance possible. A hash function can convert any input string of variable length into a fixed length string through mathematical operations. For example, if the input value is false, the hash operation output might be an 8-digit random number like DFCD 3454. A hash function is a one-way function, easy to compute, but hard to reverse. Blockchain technology uses the SHA 256 encryption hash algorithm. A hash pointer is a special data structure that not only contains a pointer to the data storage location, but also includes the hash value of that data. This structure allows verification of whether the pointed data has been tampered with. A blockchain can be viewed as a linked list that uses hash pointers. Consecutive blocks are connected by hash chains. Each block relies on the hash value of the previous block, forming an inseparable chain. Each block not only contains data, but also includes a hash pointer to the previous block. In practical blockchain systems, the so-called hash pointer usually only contains the hash value and not the actual memory pointer. Blocks are typically stored in key value databases, with the hash value as a key and the block content as a value. This method allows for quick lookup and verification of blocks via hash values. Blocks only need to keep the hash pointer of the last block in the chain to verify the integrity of the entire chain. This greatly simplifies the data verification process and improves efficiency. The use of hash pointers makes the blockchain highly tamper-resistant. If a tanker tries to modify the data in a block, since subsequent blocks store the hash value of the previous block, such modification would be immediately detected. To successfully tamper with the data, the tanker would need to modify the hash values of all subsequent blocks, which is practically impossible. The use of hash pointers helps achieve the decentralization feature of blockchain, reducing trust costs. It allows participants in the network to independently verify the integrity of the data without relying on a central authority. Public and private keys are core components of asymmetric encryption technology in blockchain. They play a critical role in ensuring transaction security and user identity verification. A private key is a randomly generated string of numbers that must be kept strictly confidential. Once lost, it can result in the permanent loss of assets. A public key is derived from the private key using asymmetric encryption algorithms and can be publicly shared. The public key is used for encryption, while the private key is used for decryption. It is computationally infeasible to derive the private key from the public key. The private key is used to sign transactions and prove asset ownership. With a private key signature, others can use a public key to verify the authenticity of the signature. The public key is used to verify transaction signatures and generate receiving addresses. Messages encrypted with a public key can only be decrypted by the holder of the private key. The private key is the master key to digital assets and must be kept carefully. The public key can be safely shared for receiving assets and verifying transactions. The use of public and private keys ensures the security, immutability, and anonymity of blockchain transactions. They are fundamental to blockchain technology. The P2P, peer-to-peer network, is a key component of blockchain technology. The blockchain network adopts a P2P model of decentralized structure with no central server. All nodes have equal status and communicate directly with each other. The P2P network is located at the network layer in the blockchain structure, responsible for the dissemination, verification, and exchange of information between nodes. New blocks are propagated through the network via broadcasting, and the receiving nodes independently verify the blocks before forwarding them. The P2P network has high fault tolerance. Resources are distributed among all nodes, so single node failure does not affect the entire network. It has self-regulation capabilities, and the joining or leaving of nodes does not impact network operations. The P2P network prevents single-point attacks, with data stored on multiple nodes to avoid data loss from single-point failures. The P2P network provides the blockchain with decentralized, fault-tolerant, secure, and reliable underlying network support, making it an indispensable core component of blockchain technology. Traditional centralized storage. Data is centrally stored on one or a few central servers. A centralized organization controls and manages the data. There is a risk of single-point failure. Server downtime may lead to data loss. Data may be tampered with without easy detection. Scalability is limited by the performance of the central server. Data change records may be incomplete. Maintaining high-performance central server is costly. Data can only be accessed through the central server. Blockchain distributed storage. Data is dispersed across the multiple nodes in the network. Data is maintained collectively by the entire network, with no single control point. Data is distributed across multiple nodes, significantly reducing the risk of data loss. Encryption and consensus mechanisms ensure the data immutability. All data changes are traceable, forming a complete history. By utilizing the idle storage resources, storage costs may be reduced. Data can be accessed through any nodes in the network. Blockchain distributed storage provides a new storage model with higher security, reliability, and transparency. It effectively addresses issues faced by centralized storage, such as data silos and single-point failures. offering new possibilities for secure storage and efficient data flow. A block typically consists of the hash value of the previous block, timestamp, transaction data, its own hash value. Each block contains the hash value of the previous block, creating an encrypted link between adjacent blocks. This link ensures the order of blocks and the immutability of recorded data. The first block, called the genesis block, starts its chain. Subsequent blocks are added by including the hash value of the previous block, forming an ordered chain of blocks. Once a block is successfully linked, it becomes nearly impossible to change the data within it, as this would require recalculating and altering the hash value of the subsequent blocks. This encrypted chain forms the blockchain, creating a tamper-resistant, highly secure, and transparent decentralized ledger. To explain the basic principles of blockchain and cryptocurrency, we use Goofy Coin as an example. Goofy Coin is a simplified cryptocurrency model. Goofy Coin creation rules. Only Goofy can create new coins, and newly created coins initially belong to Goofy. When creating new coins, Goofy generates a unique coin ID and a digital signature for everyone to verify. Goofy Coin transaction mechanism. Anyone who owns the coin can transfer it to someone else. To transfer, the sender needs to provide the hash pointer of the coin, a statement indicating the transfer to the recipient. For example, transfer this Goofy Coin to X, where X is the recipient's public key, the sender's digital signature, signed with the sender's private key. Goofy Coin ownership verification rules. The recipient can prove ownership by providing the complete transaction data structure. Anyone can confirm the validity of the coin by tracking the transaction chain and verifying each step's signature. However, Goofy Coin has a serious security flaw, the double spending attack. For example, suppose Alice owns a Goofy Coin. She transfers the coin to Bob, generating a valid transaction. Simultaneously, she transfers the same coin to Chuck, generating another valid transaction. Both transactions are valid because they contain the correct hash pointer, transfer statement, and Alice's valid signature. The root cause of the double spending problem is the lack of global transaction history in the Goofy Coin system. The system relies on each recipient independently verifying the transaction chain, rather than having a network-wide consensus. There is no mechanism to detect or prevent double payments of the same coin, making each transaction appear valid in isolation. Without a central authority or shared ledger to record and verify all transactions, recipients cannot be sure if the coins received have already been spent, undermining the trust in the system and leading to issues like currency supply uncertainty and inflation. To solve the double spending problem, the following mechanisms are introduced. First, recording the global transaction history through a blockchain. Second, introducing a consensus mechanism to verify the validity of transactions. Third, using timestamps or serial numbers to determine the order of transactions. the process of obtaining cryptocurrencies like Bitcoin, Ether, etc. by performing proof of work or similar computer algorithms is called mining. Network nodes responsible for validating transactions and creating new blocks are called miners. To add a block to the blockchain, miners first gather the transactions from the previous block and use the hashcash SHA-256 function to perform complex mathematical calculations with the previous block's hash value. They derive a new block's hash value to validate the transactions and package them into the new block. The first miner to solve the problem can add the new block to the blockchain and receives a block reward in cryptocurrency. Nonce is short for number only used once, and in cryptocurrency mining, it refers to a random number used only once. Changing the nonce changes the entire block's hash value. Miners try different nonce values to generate a block hash that meets the mining difficulty requirement. The mining process involves adjusting the nonce value until a hash value that meets the difficulty requirement. For example, starting with a specific number of zeros is found. This process proves that miners have performed computational work, making it difficult for attackers to forge blocks. The nonce is a key concept in the mining process, enabling miners to meet the network's difficulty requirements and achieve the proof-of-work mechanism. Next, we'll construct a simple example of a student grades blockchain to illustrate the mining process. Student identities are hidden, and each student has a public key matching a private key only they know. The faculty acts as miners and network nodes, responsible for mining, verifying blocks, and voting. Students' grades in various subjects from the database. Each grade contains 3 data points: subject name, student's public key, and grade. The faculty, acting as miners, verify and publish student grades through mining. Mining involves calculating a hash value using mathematical operations. Only grades with correct hash values are considered valid and published on the blockchain. In this example, the hash calculation formula is hash value equals nonce plus A plus B plus C minus last 2 digits of the previous hash. The resulting hash value must be divisible by 3. Here, A is the numerical value of the first letter of the course name. B is the numeric value of the first letter of the student's public key. C is the numeric value of the grade letter. Nonce is a random number between 1, 2, 3. For instance, the Genesis block's hash value is set to 212, and it contains no data. The first block contains data as shown in the video. The hash value is calculated as hash value equals nonce plus 80 plus 65 plus 70 minus 12. Miners iterate through nonce values from 1 to 3, calculating the hash value that can be divisible by 3. One powerful miner calculates the result first. When nonce is set to 1, the hash value is 204, divisible by 3, and meets the rule's requirement. The first miner to calculate the hash value packages it with the data into a block and publishes it on the blockchain. Other miners verify and vote, confirming the hash value's correctness. If correct, the block is valid and published on the blockchain, and the miner receives a block reward. Similarly, the second block is mined, and the hash value is 198. After verification and voting, it is also published on the blockchain. What happens if a student privately changes their grade? For example, if the student in block 1 changes their grade from F to another grade, the hash value of block 1 changes from 204. Consequently, the previous hash value in the block 2 is no longer 04, requiring block 2's hash value to change from 198, and so on. The student must change the hash values of all subsequent blocks to meet the rule's requirements, which is nearly impossible in a distributed network. This is the tamper-proof nature of blockchain. Mining difficulty refers to the computational complexity required to create new blocks in the blockchain network. As technology advances and computing power increases, block generation speed accelerates. To control the block generation speed, maintain network stability, and prevent inflation, Satoshi Nakamoto introduced the concept of mining difficulty. Most blockchain networks periodically adjust difficulty to control cryptocurrency issuance speed. Bitcoin adjusts difficulty every 2060 blocks, approximately every 2 weeks, to stabilize the block time at 10 minutes. Mining has evolved from personal computers CPUs to GPUs and FPGA chips. Now, only specialized ASIC chips meet the mining difficulty requirements. Increased difficulty means miners need more computing power to mine successfully, leading to the formation of mining pools. Mining pools aggregate computing resources to increase the probability of finding blocks and distribute rewards based on each miner's contribution. This method helps individual miners with insufficient computing power to mine independently, providing them with more stable income. However, mining pools rely on pool operators, and large pools may centralize too much computing power, posing security risks and centralization concerns. Bitcoin mining rewards halve every 210,000 blocks, approximately every 4 years. The recent block reward has decreased from 50 BTC to 3.125 BTC by 2024. As mining difficulty increases yearly, equipment and electricity costs rise. Competition intensifies, and Bitcoin price fluctuations directly impact mining profitability. The proof-of-work mechanism entails significant energy consumption and environmental impact. Although proof-of-work excels in security, it faces challenges, pushing the industry to explore more sustainable alternatives. Proof-of-stake (POS) is a consensus algorithm for blockchain networks. Unlike POW, POS determines who has the right to validate new blocks and receive rewards by holding and locking cryptocurrencies. Advantages. First, energy efficiency. POS does not rely on extensive computing power, significantly reducing energy consumption and environmental impact. Second, decentralization. POS can better prevent the concentration of computing power in a few mining pools, promoting network decentralization. Third, Security. POS uses economic incentives and punishment mechanisms, such as slashing, to ensure network security, with malicious actors losing their stake assets. Fourth, economic sustainability. POS relies more on transaction fees than block rewards, maintaining economic incentives even as block rewards decrease. Disadvantages. First, initial distribution. Early holders of large amount of cryptocurrency may gain more stakes, leading to wealth concentration. Second, rich get richer effect. Wealthier participants are more likely to be chosen to validate blocks, increasing their stakes and further concentrating wealth. Third, complexity. Implementing and maintaining POS mechanisms is relatively complex, requiring higher technical levels and security measures. POS offers a more sustainable consensus solution for blockchain by reducing energy consumption and enhancing decentralization. However, it faces challenges, initial distribution, and wealth concentration, needing continuous optimization and improvement. Altcoins refer to all cryptocurrencies other than Bitcoin, usually offering different functionalities or use cases. As of June 2024, the market value of altcoins is approximately $1.2 trillion. Ethereum is the largest altcoin by market cap, followed by Tether, USDT, and BNB. Some altcoins explore new applications, such as DeFi and NFT fields. Altcoins bring diversity and innovation to the cryptocurrency ecosystem, but also come with higher risks and volatility. Blockchain technology can be divided into three main types: public, private, and consortium blockchains. Each type of blockchain has specific uses and advantages, with a choice depending on the application scenario, security needs, performance requirements, and participant characteristics. If you enjoy this content, please like and follow. See you in the next episode.